Okay, so what we're going to do today is to look at the differences in astigmatism. We're going to look at how astigmatism can be represented, but this is not the only way to represent it, right? So I'm going to show you different ways that it shows up on our patient case sheets. So as I said, right, different types of astigmatism. It's not just regular and irregular. We can also talk about posterior corneal astigmatism and lenticular astigmatism. So there are many different types of astigmatism. We talk about how do you transpose plus and minus cylinder notation. So this is representing astigmatism on spectacles. But again, this is only one way of representing it. And I'm going to explain what plus and minus represents, or how is it significant to us. And how do you convert prescriptions to spherical equivalent? So spherical equivalent is a solution to astigmatism. It's not correcting the astigmatism to 100%, but there's a way to minimize the effects of astigmatism through using this equivalent. And then we'll talk about the different ways of correcting astigmatism. Of course, this is not the only method, but there are also other methods of correction. Which one as well? So when we talk about astigmatism, there is we talk about many types of astigmatism, but for this we're going to focus on most of the time. We're going to be interested in correcting. Okay, so when we talk about astigmatism, we need to look at the different axes where the astigmatism could exist, right? So from 0 to 180 degrees, right? It's always measured in a counterclockwise direction. Whether it's the right eye or the left eye, it always goes in counterclockwise direction. And we frequently refer to the astigmatism as the steep meridian or the flat meridian. So mainly what that means is the steep meridian is where you get more refracting power. The flat meridian is where you get less refracting power. Right? So when you have more refracting power versus axis that's less refracting, then you get to split focus. So what does astigmatism cause? It causes the vision to be distorted, right, and blurred. So this is how it would look like when a patient has got astigmatism. It will affect the visual acuity to a certain extent. If you have large amounts of astigmatism, like more than 0.75 diopters of corneal astigmatism, then it's going to be significantly affecting your visual acuity. Alright, so there is certain amounts of astigmatism that individuals can tolerate. So less than 0.75 diopters corneal astigmatism is what's going to be tolerable. And when we talk about the different types of astigmatism, so we have lenticular astigmatism, so astigmatism happening on the lens, and then we have astigmatism happening on the cornea. Okay, so I just want to show you, I'm not sure if you understood that, but switch screens here. Okay, do you see my app on Paint?
Yeah.
Okay, so I just want to show to you what I mean by astigmatism can happen on different surfaces. So if you have a cornea, right, and the eye, right, and the lens, okay, so astigmatism can happen on the anterior side of the cornea, over here, right? Astigmatism can also happen on the posterior side of the cornea over here. Okay. Posterior cornea astigmatism, and then of course you have astigmatism on the lens that can happen as well. Okay, so those are the different parts of the optical system that can create problems, right, with astigmatism. Let's switch back. Okay. Alright, so a little bit about posterior cornea astigmatism, right? So why is that important? It's important because when you're correcting the cornea astigmatism with a toric IOL, you need to consider both the anterior and posterior surfaces, right? So posterior cornea astigmatism, right, accounts for about 85% of the corneas, right? So you have this posterior cornea astigmatism that's against the rule. Okay, and the average amount of astigmatism is about 0.3 diopters of against the rule when it comes to posterior cornea astigmatism. Okay, so this is something we need to be aware of. We need to be able to correct. Just give you another idea, right? So we said that the average posterior cornea astigmatism is 0.3 diopters. So I want to show you where that source came from. Right. So this is a study of posterior cornea astigmatism performed by Douglas Cock, and this is where we base our Baylor nomogram on and what is used in our toric calculator. Right. So if you look at the mean cornea astigmatism, it was minus 0.3 diopters. I just want to show you something here about the range. So look at that here. The range of astigmatism is between minus 0.26 to minus 0.78 diopters. Right. So the mean was 0.3 diopters, but just wanted to show you that the amount of corneal astigmatism on the posterior surface can be quite significant. Yeah. And this is for this was for stated here. Mm, 86% of the patients. 86% of the eyes measured. 86.6% of the eyes measured. Okay, so just want to give you some further insight about posterior cornea astigmatism. So why is it significant for us in terms of cornea astigmatism? The thing is, when we are dealing with cataract removal, eventually the lens is removed, and what we are dealing with is only the cornea astigmatism. Okay. So if I switch. so if we are having cataract surgery performed, eventually what's going to happen is this is going to be removed. Okay. So what needs to be considered then is just the cornea astigmatism. The lenticular astigmatism, it's going to be gone, all right, because we're going to remove it by the cataract procedure. Right, so when we are calculating the toric lens, we need to consider anterior cornea and posterior cornea astigmatism. Okay, so how do we represent how do we show the astigmatism? Right, so if it's regular astigmatism, you can show it in terms of the cornea topography. Right. So when we talk about regular astigmatism, there are basically three types: with the rule, against the rule, and oblique astigmatism. And regular astigmatism can be corrected with toric IOLs. So if you look at the topographic map, the hot colors, usually what we call the hot colors are the red, and then the cold colors are the blue. So if you see a bow tie shape with the hot in the vertical meridian, so the bow tie in the vertical meridian, then this is with the rule, because the steep axis is on the vertical side of the cornea. Against the rule astigmatism, right, when the bow tie is horizontal, so the steep meridian is on the horizontal, right, so you get against the rule astigmatism. Oblique astigmatism is when the astigmatism is neither vertical or horizontal. Neither vertical nor horizontal. So it's somewhere in between the two. We call that oblique astigmatism. Okay. So how do you define oblique? Right. So when it's horizontal, 180 degrees plus minus 20 degrees. Right. So up and down 20 degrees. If it's with the rule, 90 degrees and plus minus 20 degrees on either side. Okay. So anything between 110 to 160, right, or 70 to 100, 70 to 20 degrees, that's considered oblique astigmatism. Okay, oblique astigmatism. Now the other type of astigmatism we refer to the against the rule, the irregular astigmatism. Alright, when it appears on topography, it doesn't look like a bow tie shape. It looks more like a little island. Alright, so this is just one example of irregular astigmatism that can happen. Right, so you have this steepening on a very specific part of the cornea. Right, this is what is known as keratoconus. Right, so this kind of astigmatism, you have typically more than 3 different axes. Alright, so this causes a lot of problem with the vision. Right, it's very hard to correct this kind of astigmatism because you can't do it with toric IOL. You can't do it with surgical incisions. Right, but you can do it. You can do correction in other ways. So, but even spectacles could not correct this, and even soft contact lenses would not be able to correct this. Right? But if you're using hard contact lenses, then you would be able to correct this problem. There are other types of irregular astigmatism. It's not shown here, but I can give you some other examples here. It's up here. Some other forms of astigmatism. So even if it's regular astigmatism, sometimes it can be asymmetric, right? So meaning one side has a little bit more curvature than the other. This is also a little bit tricky. Irregular astigmatism, so like this. So you can see this is more like a bent bow tie. So it's not a specific area that is steepening, but it's like a bow tie, but it's bent. Yeah, so this one is what I showed you earlier, keratoconus. Yeah, and these are some other examples of irregular astigmatism, right? So you see very odd kind of steepening in a specific area, not like a bow tie shape. Right, so these are just some examples of topography, right? But the key is when you spot something that's not regular, that looks like, like this regular bow tie shape, then, it's something that may be classified as irregular astigmatism. Okay, so the prevalence of astigmatism, so we're talking about regular astigmatism here, because regular astigmatism forms the bulk of the cases. Irregular astigmatism is quite rare, right? Occasionally you will still see it, but for regular astigmatism, you have quite a high rate of prevalence. So in this example here, you can see that cornea astigmatism is quite high quite high in the population, quite prevalent in the population. Like if you look at this cornea astigmatism that has more than one diopter astigmatism, that's already 36% of the population, right? So as we said earlier on, anything that's more than 0.75 diopters of cornea astigmatism is going to be significant, and you may want to find a way to treat it, right? So most doctors will look at that as the threshold, right? So if you look at this graph, that means more than 36% of the population would need some kind of correction for the astigmatism. So how do we represent astigmatism? Okay, so astigmatism can be represented simply, right, by spectacle correction, right? So when we talk about spectacle correction, we talk about it as spherocylindrical lenses, right? Spectacle correction. So when we look at correction of astigmatism using sphere and cylinder, it is using two different types of lenses. One is a spherical surface and the other one is a cylindrical surface. But eventually what you want to do is to be able to have correction on two different axes, right? So for astigmatism, as I said earlier on, you have two different axes of different power. You want to bring both of these focal points to the retina, so you need to find a way to have a optical correction for two different axes. Alright, so one of the ways to correct astigmatism or to represent astigmatism is using spherocylindrical lenses. Okay, so when we look at spherical cylinder lenses, happens is that you're using two different types of lenses to provide the correction, right, on two axes. Are you still hearing me? This shows that my network is quite bad.
I can still hear you.
Yeah.
Okay, just give me a minute. Huh? Okay, so the interesting thing is, how do you create two different powers with a spherical lens and a cylindrical lens, right? So if you okay, so I just want to show you what a spherical lens and cylindrical lens looks like. So when it's a spherical lens, you look at a shape like this, right? Okay, this is a spherical shape, right? It means the power, it's equal across all directions. Yeah, all directions, whether it's top down, horizontal, or in any direction, the power is the same. So this is a spherical lens shape and spherical power. So you're applying power across the whole optical system in the same way. Right? But if you're using a cylinder type lens, so the cylinder lens looks like this. Okay, so I'm just giving you a very good shape of a cylinder, right? So this is like a tube, round tube, right? So you have power on one direction, right, where the curvature is, and in the other direction here, no power because it's flat. Okay. So this is how you're going to be able to, when you add this and this together, when you put a spherical lens power, and then you want to show more power on a certain direction, you're going to add in the cylindrical lens on top of it, right? And that's going to give you a little bit more power now on this side here, right? Okay, so eventually when you use a combination of spherical and cylindrical lenses, you are able to define the power on two different axes. Okay, so what is important for you all to know is that when you look at the cylinder power, that represents your astigmatism, right? And what is important for us to know is that you can switch between the plus power cylinder and minus power cylinder quite easily, right? Because it's just using different kind of cylinder power, right? So you see my camera again? Okay, so you can use plus cylinder this way, right? So that means the cylinder is having plus power, right, to add more refracting power onto this direction. Okay, now you can represent the refraction using minus cylinder. So simply, minus cylinder means that the cylinder is not convex this way, but it's concave, right? So it's minus power rather than plus power. But then you represent it in the opposite direction. For the same case, right? Instead of this way, plus cylinder, minus cylinder will be on opposite, right? So you can use different types of use plus or minus cylinder. It doesn't really matter, right? But what is important to understand is that plus cylinder, whenever you're using the plus cylinder, right? It shows you where the steep axis is. Okay, so plus cylinder represents the steep axis is at 90 degrees. And when you're using the minus cylinder, a minus cylinder represents for you the flat axis, right, in the opposite direction. Right, so this is important because when you are looking at the toric calculator and looking at the results, you want to know whether the flat axis or the steep axis is being represented. So we're going to talk about that later on. Right, so how do you transpose the refraction? I think we covered this in one of our earlier webinars, right? But the way to do the transposition is to, in order to transpose, first of all, you add the sphere and the cylinder together to get the new spherical value. Okay, so if you add +2 to +3, you get +5 here, right? Then what you do is you switch the cylinder to minus instead of plus, it becomes minus. Right, and for the axis, you're going to switch it to 90 degrees, opposite to what it was previously. So if it was 170 degrees, you subtract 90 from it, so it becomes 80. Okay, now transposition can be done likewise in the opposite way. So if you want to go from the bottom, the prescription at the bottom to the prescription at the top, you do the same method of transposition, right? Add the sphere to the cylinder, so +5 minus 3, add that together, that becomes +2, right? For cylinder, you use the same value, but you put in the opposite magnitude. So if it's -3 here, now we put in +3 here. Axis, right? So if it's less than 90, we add 90 degrees, so that becomes 90 plus 80, that becomes 170 degrees. Okay, so I'm not sure where this showed up. Okay, so let's have a little bit of practice. I want to see whether you understood transposition. Are you able to transpose this example? Can you type it out in the chat box? How do you transpose this from plus cylinder to negative cylinder? I see one person has replied. How about the rest of you? Switch this from plus cylinder to minus cylinder. How do we do that? Very good. Oh, good. Nice. I think most of you all got it, right? So good job. Yeah. Alright, so this is your, I think most of you all got this, right? Alright, so you add the two together, you get the new sphere value, so that becomes minus 2 plus 1.5, that becomes minus 0.5. Cylinder becomes the opposite of what it was, and then the axis is 90 degrees of what it was previously. So everybody seems to get it right. Thank you very much. Really good. Okay, now the other concept is spherical equivalent, right? So spherical equivalent, it's representing the focal point of the two principal meridians, right? So this is a very easy way to correct astigmatism without using cylinder powers, right? Basically what it is you are taking the average focal point of the two principal meridian. And this only works well if the astigmatism is less than 0.75 diopters. So if it's more than 0.75 diopters, the spherical equivalent may not work very well. You still need to correct then the cylinder power. Okay, so how do you derive? So basically the spherical equivalent power is deriving the center point, right? So if we are looking at okay, if we are looking at wow, what happened to my drawing? Okay. Okay, so if we are looking at the spherical equivalent, what we are doing is, we are trying to get this effect, right? So the spherical equivalent is the midpoint of the two focal points, right? That is the spherical equivalent power. So just using a spherical lens, right, to correct the astigmatism. So rather than using a spheral cylindrical lens, you're going to use just a spherical lens to correct the to give the best result in the visual outcome. Okay, so when we determine the spherical equivalent power, how is it done? We're using the spherical sphere and cylinder prescription. Right, you need to take the sphere and add that to half of the cylinder. Right, so minus 2. Right, in here the example would be minus 2 plus half of 1 diopter. So that's going to give you minus 1.5 diopters, right? Because half of plus 1 is going to be plus 0.5. So when you add plus 0.5 to minus 2, that becomes minus 1.5 diopters. Okay, so same thing, are you able to calculate the spherical equivalent for the first example here? Can you all type it out? Okay, very good. Right. So, yeah, half of this, it's going to be +1. Add that to +2. That's going to be giving you a spherical equivalent of +3 diopters. Okay. So those are the rest of the examples. I think we don't need to go through that, all of that. All right. So in terms of representing astigmatism, right? So we talk about spherical equivalent of the sphere and cylinder power, right? So that helps us to represent astigmatism. But when you're looking at sphere and cylinder representation, that is a representation of astigmatism that is not specific to a certain surface of the eye, right? So when you're looking at sphere cylinder representation in the eye, that's going to represent the cornea, the anterior cornea, the posterior cornea, as well as the lens, right? If it's already in there. So it's a total cornea astigmatism that you're looking at when you look at the spherical, the sphere and cylinder correction. So when we look at, let's say a patient case sheet like this, right? When we look at some data like this, where it shows you the sphere and cylinder power, right? This sphere cylinder power represents astigmatism that is totaled up, all right? So it includes all the surfaces, anterior cornea, posterior cornea, and lenticular, right? So that doesn't really give us a, in terms of calculating, for example, toric IOL, that's not going to be a good value to follow, because when we look at toric IOLs, we want to only consider cornea astigmatism. Now the other piece of information in terms of astigmatism you can see on the patient case sheet is the K values. So the K values here, this is going to be representing for you cornea astigmatism, all right? But which part of the cornea astigmatism is this representing, right? For most keratometers, right, it's all keratometers in fact, right? They represent only the anterior cornea surface, right? So the posterior cornea surface is not represented here. Okay, so unless you're looking at some specialized instruments, so for example, the IOL Master 700, which has the capability to measure anterior and posterior cornea astigmatism, or some other instruments like the Pentacam, right, or the Galilei instrument, those instruments that use imaging, right? So that's also measuring anterior and posterior cornea astigmatism, right? So so in most cases, only the anterior cornea astigmatism is represented. Okay. Now, of course, there is also other ways to show the astigmatism. So, like I've shown you earlier on, when you look at cornea topography, right, like this, right? So sometimes topography, right, is captured, right, in the patient case notes, and you can see the K values in terms of the K1 and K2 values. So it just shows you 2 K values, right? But this is simulated K readings, right? So K readings that are simulated, right? So the reason is because for topography, the central cornea is not measured, but rather it is, the information is extrapolated from the peripheral parts of the cornea to the center. So that's why they call it simulated K readings, right? So quite often the doctors may not rely on topography right, for the K readings, but rather they look at the keratometry for more accurate central corneal readings. Okay, so in terms of surgical correction of astigmatism, you can use surgical correction, right, using incisions to manage the astigmatism. So using certain cuts on the cornea can correct astigmatism, right? So so the cuts that you make on the cornea, right? So it can be the actual phaco incision, or it can be some kind of deliberate incisions done on the surface of the cornea, right? So they call this limbo-relaxing incisions, right? So limbo-relaxing incisions are not penetrating, so they are on the surface of the cornea, right? So they don't penetrate right into the anterior chamber, right? But they are on the they cut up to 90% of the depth of the cornea. Phaco incisions, of course, are penetrating, right? But whenever you make a cut on the cornea, it's going to it's going to correct certain amounts of astigmatism or induce certain amounts of astigmatism. So let me show you what I mean by that. Okay, so if you have cornea, right, so you need to think about cornea as having a lot of these fibers, right, corneal fibers, right, so they are fibrous tissues that extend radially, right, all across, right. So what happens when you make a incision, a cut on a certain surface, right, like for example, if you make a cut here, okay, so what's going to happen is that this surface here is the fibers are going to be cut and it's going to be relaxed, right? So whenever you make a cut on the steep axis where there's more power, what's going to happen is that axis is going to have less power eventually when you make the cut. Right, so if you make a cut on the steep axis, it's going to correct the astigmatism. Right, so when it's also important to know that when you make a cut here, what happens is that opposite axis is going to steepen. So you relax this axis, but you steepen the opposite axis. Right, so the net result of the astigmatism is going to be less. Right, but the average corneal astigmatism is the average K value, right, is going to be the same, right, because the coupling effect happens in equal amounts. Okay. Right, so phaco incisions, right, they correct about 0.5 diopters of astigmatism, but that's for a 3.2 millimeter incision. Smaller incisions correct about 0.25. So nowadays I see that most surgeons are selecting this value because their incisions are usually about 2.2 or 2.4 millimeters. So the smaller incisions actually induce much less astigmatism, right? But this value needs to be decided by the physician, right? Because they know they need to be aware of how much change astigmatism their incision creates, right? So the incision construction, the way it's constructed, the size of it, of course, is a factor, but the way it's constructed, like how deep the tunnel is, right, or the actual placement of it, does have an effect on the induced astigmatism as well. So don't be surprised if some of your surgeons, even if they are doing 2.2 millimeters incisions, they may have a slightly different induced astigmatism value. Okay. So limbo relaxing incisions are a little bit more, you can correct more astigmatism because you can make a wider cut. So you're not limited to the size of the phaco incision, but for limbo relaxing incisions, you can cut a little bit more. Alright, so you can treat up to 1.5 diopters of cylinder, alright, and it's usually done, so it's done in the limbus area, right, and it's not cut through the cornea, just about 90% depth of the cornea, and meet at the steep meridian. Okay, so this can be also done at the clinic, right, with the slit lamp or intraoperatively. There is a LRI calculator that is usable, alright, so if your surgeons are thinking of using limbo relaxing incisions, there is a resource that is available for them to calculate the amount of incisions, the depth and the size of the cuts they need to make, right? And there are two nomograms in there that is available they can choose from. One is the Donenfeld nomogram, the other one is the Nichiban nomogram. So it's a choice of the surgeon, right? They will give slightly different results, but it's just going to be a starting point. So eventually, for LRIs, if doctors want to be successful in it, they may want to create their own nomograms, right? So, but again, for limbo relaxing incisions, it's not as predictable. It's not as predictable as toric IOLs, because when you make certain cuts on cornea tissue, there's always the variability of the tissue itself you're cutting, and then also the healing effect of the tissue, right? So limbo relaxing incisions are known to have a little bit of regression because of healing, right? And so it is not as predictable as toric IOLs, right? Because toric IOLs is a hard piece of acrylic material. It doesn't change over time, right? But what you need to get right is the calculations for toric IOLs. So the other ways of correcting astigmatism not mentioned here, right, could be also using laser refractive surgery, right? So laser refractive surgery, like using in LASIK or PRK, right, that also can correct the astigmatism. And I believe SMILE does not correct astigmatism. Is that right, Hannah?
It can, not a huge amount, and I'm not sure if it's actually indicated to do so, but it is being used for it.
Okay, yeah. So those are the surgical methods of correcting the astigmatism. Of course, toric implantation is another method. Non-surgical ways, all right. Of course, you have the use of spectacles. So spectacles can correct your regular kind of astigmatism, right, but not irregular astigmatism. Contact lenses, soft contact lenses will also be able to correct astigmatism, right? Regular ones, right, using soft contact lenses. For irregular astigmatism, you won't be able to use soft lenses or spectacles to correct it, right? So you need to use a hard contact lens to correct irregular astigmatism. Surgically, irregular astigmatism could not be corrected by limbal relaxing incisions or toric IOLs, right? Or any incisions, right, that you do. But irregular astigmatism can be corrected by refractive surgery, right? Laser refractive surgery, right? So LASIK, right? If you are using customized refractive surgery, customized form of refractive surgery, laser refractive surgery, you can correct irregular astigmatism. Okay, so toric IOLs is it's what we are interested to discuss here. All right, so how do we use a toric IOL to correct the astigmatism? Basically, what it does is that toric IOLs provide you with two different refracting surfaces, two different refracting axes, right? So two different powers. Let me bring up my chart, my drawing board. Okay, so are you seeing my drawing here? Not that great a drawing, but I hope you understand what I'm trying to represent here. Okay, so you see this is what is represented with an eye that is untouched with the natural lens, right? So when the cataract surgery is performed, what happens is that the lens is taken out. Okay, so you don't have any more lens in there. Okay, and what happens is that your cornea, right, if it has astigmatism, then it has two different focal points, right? And why I show the focal points, it's a little bit way back here, because there's no lens that is in place, all right? So when you choose a IOL implant, when we choose a IOL implant, oops, okay, and we put an IOL in there, what we are attempting to do is to correct the refractive power of the eye and bring the focus point forward. Okay, so when we are doing this with a regular monofocal implant, so what you can see here is a calculation, right? So when we are calculating a monofocal implant, what's happening is that we are using the K values over here, right? But we're not using a specific K1 or K2 value, but we're using the K average value, right? So somewhere between, so in the middle between K1 and K2. So we're using the K average to perform the calculation, right, to give you an IOL power like this, 21.5 diopters. Okay, so this is what we're going to get over here. All right, so let's say we put in 21 0.5 diopters of a monofocal implant, non-toric lens. Alright, so what happens is that we're not correcting the astigmatism, but because we are using the midpoint of the 2K values to perform the calculation, effectively what happens is that we bring the focus onto to as close to the back of the eye as possible, but neither one of the focal points is on the back of the eye, but rather the spherical equivalent power, right? So that is why when we look at the calculation here, right, this is always referred as the spherical equivalent outcome, right? And this is the spherical equivalent IOL power that we're putting in, right? So when we are using a standard monofocal lens, we're not correcting the astigmatism as in bringing the two focal points into one point, but we are using the spherical equivalent, right, to get the best result, right, without using a toric IOL. Okay, so like we said earlier on, you can use the spherical equivalent effectively, right, to correct the vision if provided the astigmatism is not more than 0.75 diopters. And if you look at this case here, the astigmatism here is actually quite significant, right? To take the difference here is actually 1.62 diopters of corneal astigmatism. So that's actually quite significant, right? So using the spherical equivalent power may not be perfect to correct the astigmatism, because this gap here that you see here is 1.62 diopters. So that gap here, it's a little bit too much, right? And you won't get a very good clear vision. All right, so what is needed is then we need a toric lens to correct the astigmatism here. Okay, so if you think about the cornea power here and the IOL power here, that means to say that the K value, one of the K value, right, the flatter part of the K value plus 21.5 diopters, it's too much power. Okay, too much power. So sorry, this one is more steeper. So this cornea power, which has more power, plus 21.5 diopters on the lens, has too much power. Okay, on the opposite, where the cornea power is lower, okay, when you add on that cornea power to 21.5 diopters, that is too little. All right, so that this 21.5 diopters is too little for a certain power of the cornea, and it's too much for a certain power of the cornea. Right. So when we choose a toric lens, like so probably in this case, you may choose let's say a ZCT to 225, right? Okay, so when you choose a ZCT 225 lens, okay, what it means is that you're adding 2.25 diopters, right, of cylinder power onto the lens. Okay, so what that means is you take 2.25 divided by 2, so that gives you, I think it's 1.175, right? 1.175 on either side. Let me do a calculation. 1.125, sorry. Right, so it's 1.125 on either direction. So actually for a 21.5 diopter lens, that is actually equal to a lens that is 22.625, right, on one axis, and on the other axis it is running out of room to write here, 20.375 diopters. Okay. All right. So the lens, when you use a toric lens that is ZCT225, right, it means that you have a little bit more power on one side, right, and a little bit less power on the other side. So what that's going to do, if you align the lens correctly in the eye, what it's going to do is it's going to be able to bring your two focal points, right, much closer, right, much closer together. Right, so toric IOLs help us to correct the astigmatism, right, by giving you two different refracting powers on the lens, right, to bring the two focal points closer together. So if we look at the toric calculator, so if you look at the toric calculator, so I put in the example here. Alright, so we put in the K readings. Flat K reading, it's the smaller value. Steep K reading, higher value. And remember to put in the axis. So how do I get the numbers here? Alright, so basically I took the numbers here. Flat K, steep K, and then I think the axis was represented at the back of the K sheet. So the steep K, 45.62, is at 19 degrees. So I put in 19 degrees here for the steep K, right? And the flat K is opposite of that, 109. Okay, and then this is the calculation that is derived. Right, so you need to put in the axial length as well. Axial length indicated over here. Alright, so I'm taking the immersion method of our biometry using the axial length 23.14 millimeters. And here, method of the biometry, so you can either choose, so what I choose is optical or immersion, which is the same value of 119.3, right? Spherical equivalent power chosen, 21.5, so I'm just assuming it's this value that is chosen, 21.5, closest to emmetropia, slightly myopic, but still very close to 0. And the K-index, so the K-index is something that you need to choose based on the keratometer that you're using. So in this case, I assumed it to be 1.3375. So there are other options here. You need to choose the correct index based on the keratometer model that is being used, right? And then choose either plus or minus cylinder to be shown up as your results here. So in this case, I chose plus cylinder. Alright, so plus cylinder. So it shows me the results in plus cylinder format here. So as you can tell here, the correction of the astigmatism, right, using ZCT 150 or ZCT 225, right, gave you the closest results, right, to what you want to achieve. Now, how do you interpret the results here? So remember what I said about plus or minus cylinder. When you choose plus cylinder, this shows you the results in terms of the steep axis. Right, so if you're choosing ZCT 150, the residual astigmatism is going to be plus 0.43. Okay, so that's quite a lot of reduction from what it was previously, 1.62, going down to 0.43. Right, the steep axis is now at 22 degrees. Okay, 22 degrees. So if you look at before surgery, the steep axis was at 19 degrees. So it's really close. The reason why it shifted slightly is because your incision, where it's placed, has induced some astigmatism, and because it is not exactly at where the primary axis was, it's going to shift your axis slightly. Right, it's going to shift your axis slightly. So rather than it being 19 degrees, it's now changed to 22 degrees. Okay, so this result shows that the astigmatism is quite, the axis of the astigmatism remain unchanged, right? Because the steep axis at 22, steep axis at 19 means that the incision, the axis of the astigmatism remain unchanged, but the magnitude of the astigmatism has gone down. Okay, so that means if we look at the result here, right, so remember we chose the spherical equivalent power, 21.5 diopters, right? But the result is minus 0.09. So that means the midpoint, right, is slightly myopic and at minus 0.09 diopters. So it's about, so if I just draw the line just a little bit this side, right? So slightly myopic is the midpoint, right? Because it's a 21.5 diopter lens. Now, when I correct the astigmatism, so I'm bringing the astigmatism down from 1.62, bringing it down to 0.43. All right. So what happens is that the two focal points are going to be much closer now, but the gap that you see between the two focal points, right, is 0.43 diopters. 0.43 diopters. Okay, so we have narrowed the gap from 1.62 to 0.43. So that's not a bad result, because if it's less than 0.75, that means the patient is going to see pretty good. Now the other option here, if you are choosing ZCT 225, what shows up here is that the IOL model will create an axis flip. Okay, so what that means is that you're going to switch the astigmatism axis. Okay, so if you look at the residual astigmatism here, it's much lower. It's 0.07. So the amount astigmatism is actually much lower than the choice up here, right? But what happens to the steep axis? So now the steep axis is at 112 degrees, right? Because this is a plus cylinder, right? Steep axis is at 112 degrees. So when you compare it with the original astigmatism, the steep axis is opposite. Okay, so that means it has changed the axis of the astigmatism. Okay, so what that means is that in terms of the correction that we're getting here, okay, we are getting the 2 points much closer together. Okay, so just think about this as much closer. It's just 0.16, right, diopters. Okay, so it's much closer, but what happened is that because we have corrected it so much that the two axes has exchanged places. So the focal point that was on this side here has now shifted over here, and the focal point that's on this side originally is now shifted over to the other side, right? Because there is too much correction, that's why it resulted in a flip in the astigmatism, right? A flip in the astigmatism. Okay. So the result here, there's always a preference, right, on the surgeon. They may choose not to flip the axis. Some surgeons may choose this option because it has the least amount of astigmatism, which they think it's better for the patient, right? So they want to correct the least amount astigmatism as the priority, right? So some surgeons would choose this. Right, so there are other considerations as well. So sometimes in terms of correction, they may look at the original spectacle correction. So like for example, they may look at the original correction of the spectacles, and they want to see how much is the astigmatism actually correcting. Is it fully correcting or not fully correcting what is the actual amount of astigmatism. So if the spectacle correction was not fully correcting it, they may choose not to fully correct the astigmatism, right, like this, right? So the other consideration is the shift in astigmatism. So generally what happens is that most patients start with the rule astigmatism, and as they age, it drifts towards against the rule astigmatism, right? So so some surgeons want to leave a little bit of with the rule astigmatism, right? So that as the patient age and it drifts towards against the rule, the astigmatism neutralizes itself. So some surgeons would take that into consideration as well. So sometimes you hear about doctors saying, I prefer to leave a little bit of with the rule astigmatism in there, right? So that is one of the reasons why they would choose to do that. If you look at this case here, the steep axis is at 19 degrees, so meaning that this is already against the rule. Right, so this is showing against the rule astigmatism. Right, so in this case, if the patient is already very elderly, this may have already been shifted to against the rule. So they may not consider this for this patient. Right, so for younger patients, they may consider that. The other thing to consider is posterior corneal astigmatism. So when you choose posterior corneal astigmatism here, what it does is that it incorporates the PCA into the calculation, right, to create that. So when you talk about posterior corneal astigmatism, we're talking about an average of against the rule astigmatism of 0.3 diopters, right? So if you look at the original astigmatism, it is against the rule. Now when you add posterior cornea astigmatism against the rule to what was already against the rule, the total amount of astigmatism required for correction is much higher. So that is why you see here, previously without PCA, we were overcorrecting the astigmatism. But when you include PCA, we are now not overcorrecting it. We are slightly undercorrecting it with the same ZCT225 lens, right? So this does work, right? So the good thing about the new calculator website is that under the preferences support, you can choose to turn this on by default, right, or turn it off, right? So if your surgeons are mainly using keratometry readings without measuring the posterior cornea astigmatism, you may want to switch this on, right? Because oops, it took away my calculation, right? So if you are using instruments that do not measure posterior cornea, then you may want to turn this on, right? But if the surgeon is using instruments that include posterior cornea astigmatism, then you can turn this off, right? Because whatever you input as your K readings here, all right, you would have assumed that it has taken posterior cornea into its consideration, right? So some instruments, like I said earlier on, some OCT instruments like your IOL Master 700 does have the potential to measure posterior cornea astigmatism. Some sham fluid imaging instruments, right, like Pentacam or Galilei, they can include posterior cornea, right, or some kind of topography, like the one from Bosch and Lomb, I think they're using, it's called the Xioptics. What is the instrument called? The Bosch and Lomb instrument for measuring cornea, right? Anyway, there are some topography that can offer posterior cornea astigmatism measurement as well. Okay, so the thing about toric lenses is that you need to make sure that in terms of alignment it is perfect, right? So any loss of alignment, all right, is going to undercorrect the astigmatism. Every degree of off-axis rotation gives you a 3.3% of cylinder reduction correction in terms of cylinder power, right? So if you have 15 degrees of misalignment, then that's almost half of the cylinder correction is gone. Okay. All right. I think that's it. I have to share with you today. It's a little bit of overrun, but maybe we can have any questions or comments from you guys.
Hi, Melvin.
Hi.
Great job. There is one question in the chat box. If you could have a look.
Let me look at it.
Now. How do we know whether they include PCA in the measurement when reading the biometry, for example, with IOL Master 700?
How do we know whether they include PCA in the measurement when reading biometry?
Yeah.
Yeah, I think that the best way to do it is, I think you need to ask the person that has done the measurement, right, to see whether they have included posterior cornea, right? I think what they use in the IOL Master 700, the terminology they use is TK, total cornea, total keratometry, right? So I've not seen the 700 printout, but what I know about the terminology they use for the posterior and anterior measurement, it's total keratometry reading. Yeah.
Okay. Yeah, so Yinghui is asking, if doctor uses IOL master, would you use K values or TK values for IOL calculation?
Yeah, the IOL calculation itself, right? There is a modified formula. So whatever formulas that we were using in the past, like Barrett or SRKT or whatever formulas that we were using, when they are using the TK values, there is a modified TK formula. So for example, SRKT, TK, and there's a Barrett 2 TK formula as well. So they do have a little bit of modification on the formulas itself when it comes to the IOL Master 700, and they're using the TK values. So you need to pick the right formula, right? So it's SRKT TK or Barrett 2 Barrett Universal 2 unit formula, not just the regular Barrett formula or the regular SRK.
Great. Thank you, Melvin.
Yeah.
That's it, I think, for the questions in the chat box. Does anybody on the call have any questions? Cindy's just typed one in. If the surgeon wants to set a cutoff to decide whether this patient needs a toric lens. Oh, is that an answer? No. Should we look at delta K or TK?
Well, I mean, I think it would be better to look at TK. I mean, you want to look at the total cornea astigmatism to be sure, because like we said, the threshold for cornea astigmatism is 0.75 diopters, right? So post-operatively, if they can bring the astigmatism down below 0.75 diopters, including posterior and anterior cornea, right, then that would be good, right? So previously, when you are just looking at traditional keratometry readings, it's a little bit of a guess, right? So that means if they're looking at the K values from a traditional keratometer, they need to mentally add in some posterior cornea astigmatism. All right. So for example, if you're looking at against the rule astigmatism from the keratometry readings, then mentally they need to add in a little bit more astigmatism, because we know that the PCA is going to be against the rule as well. So you want to add in a little bit more astigmatism to think about whether he can bring it down below 0.75, right? So if you have the total cornea astigmatism, that will be easier to get that idea, right, about whether they need to correct it or not.